This is an exciting moment in the history of metamaterials. We would like to think so. But joking aside, you're here to witness, we feel, a good occasion, an occasion where we're launching the Metamaterials Innovation Network, focusing on commercializing the great work that's been done in the last few decades by our excellent researchers in this area. As KTN, we've been looking at this area for a number of years, and we've been watching the developments that have been happening within our academic base, their efforts to commercialize their work, and we felt there's enough evidence to make a case to inside KTN and to Innovate UK to provide dedicated funding for us to do a number of activities. And here we are today to launch this exciting moment to you all, for you to engage in this activity to realize our dreams of creating wealth and having social well-being from the use of metamaterials. So thank you for joining us, and thank you for my panel of speakers. Quite an excellent panel who will take you through the history of metamaterials and examples of what we've been doing and the exciting future that awaits us. So we have a busy agenda and a lot to go through, but we'll have a break later on, and you can come back and do a one-to-one online networking. So do remember to sign up for it. You have the opportunity during the lunchtime to decide where you want to place your questions. So please, there will be no questions at the end of the talks, so that we can just flow from one question to the other, from one presentation to the other. Regard this morning session as informational session, a session to take you through the excellent work that's been taking place, explain to you what the Innovation Network will be doing for metamaterials and how you can get engaged. And if you have any questions, at the bottom of your screen, you'll find the Q&A box. Just pop your question in there. And if we collect many, we will make sure that we might want to arrange a question time session another day and discuss the answers to those openly. Otherwise, we will share those questions with the speakers who will address these during the online networking sessions. So you will have a pick of speaker that you want to speak with to address your question. But share it and give us an idea in terms of what you would like to know more about. If you have an IT problem, we will encourage you to pop your question on the chat box. A bit about innovation networks and KTN. The aim is to convene people who will not normally meet around some interesting subject, to learn about those subjects, connect and explore the opportunities those subjects offer. We used to call this special interest group until recently, and as part of our rebranding in KTN, they're now known as Innovation Networks. So some of you would have interacted with us in special interest group days, but they are similar in nature and focused in the same way. We have 15 innovation networks running now. These are run by the KTN, and we have in the materials area, we've had 4 successful ones in the last 5 years. The most recent one is commercializing graphene and other 2D materials. And during which time we interacted widely with the community to share your ideas in terms of how we will be able and what we need to do to commercialize these. Similarly, our focus for today and for the next 2 years, we'll be looking at metamaterials. So this launch event is taking place really to tell you more about this innovation network and why we think the time is right to look forward to an exciting future. We want your input. We want you to continue contributing to the creation of wealth and well-being for the UK, because we think there are opportunities, exciting ones, that metamaterials can offer us. So for those of you who are new to metamaterials, welcome. We want you to be involved. We want you to help us on this journey. For those of you who've been working on metamaterials, you know all about it, but we want to raise the awareness, that we want to take you on a different journey, a journey that commercializes your ideas. Work with us. So what are metamaterials, you will ask? They are artificially made functional materials. They're engineered to exhibit unique electromagnetic and acoustic properties. They enable devices to achieve much higher performance and efficiency than we can achieve now. And the growth potential forecasted pre-COVID because the 10.7 billion globally by 2030 will need to be flexed. That exercise hasn't been done, but we're watching the brief to see how much COVID has actually impacted on the developers in this area. But that 10.7 billion globally is worth tapping into. And examples are, and these are exciting applications, 5G networks, autonomous and connected vehicles, these are not going away, antennae, sensors, managing sound, vibration dampening, energy harvesting, wireless charging, and you hear case studies on some of these today. So what's been stopping metamaterials from being commercialized if these exciting opportunities exist? They've been somehow well understood by those who work on it, those who are new to it, and many who could make use of it, run a business on it, don't really fully understand it. And because of that, the size of the operations we have in the UK suggests that to fully commercialize these and to create the impact that metamaterials can create, will require quite sizable resources to deliver those useful products. It requires skills and expertise that are difficult to find, but we do have centers of doctoral training, producing PhDs who've been doing research in this area. So there are a number of trailblazing skill sets that are there, but they need to be grown further. We need a supply chain that's resilient, and a UK supply chain that can take on board the requirements of metamaterials and assure the industry, the user industry, that they can be readily available for their needs. There's more fundamental R&D that needs to be done to finesse what has already been done and to create a pipeline of innovation opportunities. But we do have a large portfolio of R&D outputs from the work that's already been done, and we need to translate these into timely products and services. So to sum those barriers up, we say we have excellent academic research in this field, and you just have to search citations, publications, and patents filed, and you will find that the UK actually is among the top 5. But you look at industrial uptake and the industrialization process, and apart from defense sector applications, we're quite poor and we lag behind. So we need to do something, hence the focus of this Metamaterials Innovation Network on commercialization, what we've got. So the network is a 2-year project being run by KTN. It's supported by Innovate UK to ensure successful commercial exploitation and technology transfer from the research base and the spin-outs that have been formed through collaboration, brokered or encouraged. And what we want to do is to work across the whole value chain to identify and exploit the commercial opportunities that are there, identify those low-hanging fruits, and see what we need to do to actually bring them to market. Build a community of innovators, promote the knowledge and the technology transfer processes for metamaterials, encourage and engage product designers, manufacturing, investors, and end users to make more of metamaterials. We want to build valuable collaborations to develop applications using metamaterials, and we want to engage investors to help deliver these by investing more on a large scale in the exploitation of metamaterials. But to do this, we want to focus. And we've done our homework, and there are a number of sectors that have potential products from the research portfolio that's there, making use of the different types of metamaterials that have been developed. The construction sector, particularly focusing on acoustic metamaterials, but there are communications, systems, consumer electronics that can be embedded in smart systems within the construction area. There is 5G opportunities for antenna and electromagnetic metamaterials. Defense and security, a lot is being done in that area. Medical and healthcare systems, and you get a case study on how the medical sector is being encouraged to use metamaterials. The transport sector, and we've already talked about autonomous and connected vehicles, and consumer electronics, energy and power, energy harvesting. So there's a lot there, and a lot of sectors with growth potential and forecasted growth in the UK and globally that we can tap into. So what's our approach as an innovation network run by the KTN? We want to work with the R&D base to define what the value proposition is or should be. We want to run that value proposition past the market and investors to validate and make sure we're thinking the right way, and it's a go. We want to support the spin-outs who are already on this journey of commercialization, SMEs to scale up. So what is needed to support them, either through private equity, through technology input, through public funding, to encourage them on their scale-up process. We want to engage specialist support groups, IP providers, offices, IP solicitors, metrology and standards communities to support this area. We want to engage the OEMs and the end users who make products and supply products and use products to learn about metamaterials and to invest in the potential applications we feel they offer. And we want to learn overseas. We know China, the USA, and Japan are exploiting metamaterials. We want to understand what they're doing. We want to benchmark and position the UK. And we want to provide opportunities for export of products made from metamaterials to other countries that believe in it. Very important to KTN is our ability to connect across different sectors, to encourage collaboration. And we do this because we have a wide breadth of expertise and we cover a large number of sectors, as you can see here. We have a large number of organizations, 60,000 and counting, signing up to the KTN and actively supporting what KTN does. And this is made up of 90,000 individuals. So it's a large pool to pull on. and different sectors to tap into, different technologies to cross over, and to support our drive to commercialize metamaterials. And the KTN delivery team has myself and Tatiana as co-lead, Darren as our project manager, Poonam, who've been communicating with you, as our events manager, and Sasha as our marketing manager. So this is the core team, but in the true sense of tapping into our cross-sector collaboration and expertise, we have a number of colleagues who've signed up to support our efforts in commercializing metamaterials. Hazel, focusing on defense and security. Lingwin on sensors. Mark, interacting with other emerging technologies. Paul on enabling technologies. Sven on electronic systems. Phil, looking at ICT, artificial intelligence, robotics, and taking a systems approach and supporting us with that. Michelle on transport. Martin on health applications. Emma playing a key role in our training, in our access to finance, investors, and raising the awareness of the investor community here. And John, who you hear from later on today, on design and innovation, and how the design community, how we work with them through our MADE partnership program to engage on breakthrough technologies such as metamaterials. We're not working alone. We have scrutiny, we have steer, and we're guided by an advisory board. A few years ago, we helped set up the UK Metamaterials Innovation Group, and in making the case and providing the evidence to create this innovation network, we relied heavily on this leadership group who provided us with the evidence, the confidence for us to make our case within KTN and to Innovate UK. This is an area we're supporting. We are recruiting additional members from communities who can benefit from metamaterials, but so far are not as close as the leadership group. So we're recruiting from OEMs, from end users, and from the investor communities. We have a progress review panel internally within KTN who reviews our progress. We report to the KTN execs on what we're doing and to our Innovate UK sponsors. But most importantly, the advisory board contribution is important. The progress review is important. But very important is really checking the integrity of the tasks we do. The task we set ourselves as a network. The integrity of that is reviewed through our peer interactions and through your contributions. So we create a program, finesse a program with your help. And then over the next 2 years, we will be in constant contact with you to develop and to grow and achieve our aim of commercializing metamaterials. In summary then, today is a call to do battle, more than just to arm. We are ready for battle. And the battle is to create wealth and well-being for UK from using metamaterials. We have the people and expertise. We want to be able to harness the knowledge about metamaterials, communicate, disseminate this. We want to look at the life cycle and sustainability issues and the impact metamaterials will create. We want to look at engineering and product design, engagement and issues that may arise during scale-up. We want to look at production and processing technologies that will help to bring this product to market. And last but not least, we want to make sure that the innovators, the developers in this area are well prepared to present their case to raise funds, and they are investor ready. And we want our program to engage with the specialist support I spoke about earlier, the IP, the metrology, standards, environmental and health and safety specialists. So we look forward to you joining this journey towards a positive change for the UK using metamaterial. Sign up, we will be in touch, you're on our delegate list, so you get a copy of this slide and you'll be able to contact us. Thank you, enjoy the rest of the day, and I'll hand over to Ian, who will tell you all about metamaterials past and present.
So thank you, Robert. It's a great privilege to have the opportunity to address the audience today on this subject as a member of the Metamaterials Leadership Group. So my name is, good morning everyone, my name is Ian Youngs. I'm a Senior Fellow at DSTL, the Defence and Security, the Defence Science and Technology Laboratory of the Ministry of Defence. So this puts me in a really good situation to provide somewhat of an independent, or at least an independent view, or at least a view that is driven in the national interest to support this initiative. And today feels really very timely, especially as we as a country await renewed direction from the comprehensive spending and integrated reviews that our government's undertaking. And what's kind of clear from that already is the expectation of greater cooperation across government departments to meet the complex needs across defence, civilian and societal issues for our country, and to think about its position in the world. So amongst that, there's obviously the very important role of research, technology and innovation, and that being emphasised, not least from the recently published National R&D Roadmap. So it's in that capacity that I was invited to provide you with some context, as Robert said, to reflect on the journey of metamaterials to today, perhaps the strategic purpose and the goal. But of course, there was research in these sorts of areas before we encountered the term of metamaterials. And so how have I found myself in this position? And whilst the world now got a set of materials classified as metamaterials, well, I became part of this endeavour in 1990 when I started my first job in the defence sector. And for me, an objective was to understand how emerging computational electromagnetic modelling methods, like finite elements, might enable the discovery and optimisation of higher performing radar absorbers. Now, part of this work, which we're undertaking with GC Marconi and Professor Sir John Pendry at Imperial College, led to the rediscovery, as is shown in this slide, of artificial materials formed of wires with micro properties very similar to that of the ionosphere. Yet the original work we later sort of reappreciated on these wire array structures stems from the 1960s, and very much built upon work of radar engineers from the Second World War. But more than that, of course, researchers over the centuries have been exploring how the path of light is affected by materials, understanding material composition at the atomic, molecular and microscopic scales, and how this relates to the observed phenomena. So what is fundamentally new with what we now class as metamaterials? It's the emergence of the same rigorous understanding of how higher scale geometry, the arrangement of those materials at fine scales, provide substantively new and beneficial degrees of freedom in design and design performance within bespoke form factors. The convergence of this knowledge with the capable modelling, simulation and design tools and advanced manufacturing methods across a diversity of length scales like additive manufacturing and nanofabrication has resulted in a tipping point to unlock game-changing opportunities, as Robert has introduced. It's also worth noting, as well as three-dimensional materials, there's an analogy to two-dimensional forms of metamaterials, often referred to as metasurfaces, and these also relate to the fields we might know, and some of you might know as plasmonics, and the ability to create artificial plasmonic structures. This also has origins in past work, and a good reference there is the paper on the genesis of corrugated electromagnesis electromagnetic surfaces by Cutler in 1994. Some of the early origins, nearly some 20 years ago now, come from US defence-funded research as well as that in the UK, and agencies like DARPA played an important role then in the development of metamaterials at that time, and indeed the term metamaterials was born in 1999. This slide shows some of those key participants in those US programs, including the program manager, Dr. Valerie Brining, who introduced the DARPA program on composite materials. The objective of that program was to develop composite materials comprised of conventional materials, but which yielded properties not found in nature due to the use of that geometry and structure. And it was Roger Walser who suggested the name of metamaterials during that program. At that time, a medium with negative permittivity and negative permeability, which I'll explain a little bit more in a second, did not exist. So the metamaterials we find today evolved from those of DARPA and the DoD programs in the first decade of this 21st century. Yet, because of the strong UK heritage to which I've just referred, the UK also has long been a global leader in the academic study of metamaterials. The field has also been reinvigorated during the last 2 decades by research from some of our most eminent academics in the UK, including Professor Sir John Pendry, who has written seminal papers on topics ranging from artificial dielectrics to transformation optics, invisibility cloaks, and negative refraction and diffraction beating imaging. So the UK has a real opportunity to play a leading role in this metamaterial revolution through metamaterial-enabled technologies. I think I skipped an extra slide there. So this slide kind of reinforces that metamaterials aren't just about invisibility, as has probably appeared quite popularly in scientific literature and press, or about negative index. It's really about extra degrees of freedom that metamaterial design introduces, allowing us to manufacture and exploit materials with bespoke electromagnetic and other properties. It's the dramatic expansion of the design space, which is characterized by charts like that shown here. In the electromagnetic sense, it's the intrinsic electromagnetic material properties used in the design of materials and components for applications such as lenses that represent the interaction of materials with electric and magnetic fields, and these being the key components of electromagnetic waves and signals. It's these properties shown on the chart of the electric permittivity, epsilon, sometimes referred to as the dielectric constant, and the magnetic permeability, mu, that define that design space. So in the top right or green quadrant, this aligns with conventional dielectric materials, which allow waves to propagate, such as in materials like glass, but there is a degree of reflection and these materials can absorb energy. The use of structure with materials with these properties is the origin, for example, of iridescent colour observed in butterflies, and also exploited in the design of multi-layer anti-reflection coatings. Materials with high magnitude properties in this space also enable the miniaturization of components, including antennas. Moving to the bottom left quadrant in cyan, this represents part of the property space that's been really trailed by the early metamaterials. It's the previously unattainable space until metamaterials were realized. Here, both material properties are simultaneously negative, and they had the so-called negative angle of refraction for light passing through these materials. Materials in this quadrant allow waves to propagate, which is also important in many applications. The combination of fine-scale geometry and structure with the chemical composition of the materials involved has enabled engineers to access a more continuous as well as expanded design space. Moving to the top left quadrant in red, this represents materials with so-called plasmonic response. Only the dielectric permittivity is negative here, and this determines when materials, like metals, are highly reflective. Metamaterial concepts lead to artificially constructed plasmonic materials with properties like the ionosphere and plasmas, charged gases. The ability to better control the propagation of waves bound to surfaces and diffractive scattering is a result from these sorts of materials. And finally, the bottom right quadrant in purple is the magnetic counterpart of the red quadrant. So this represents artificial magnetism and magnetic resonators. You can see the ferrite block in the picture, but even this doesn't show negative permeability unless we can find a high quality factor resonance at a specific frequency. So this type of material is exploitable in guiding magnetic fields, for example, in magnetic resonance imaging. And as shown in the picture, there are some recent micro and nanoscopic metamaterials and meta-atoms that are being explored to populate the design space in this quadrant. So far, I've given an indication of what metamaterials are in the context of electromagnetics, particularly in terms of visible light and microwaves. And even then, their form is highly diverse. Robert has also provided a definition and highlighted the application sectors, also very diverse. But it is vital to emphasize that new classes of metamaterials have and continue to emerge in the context of other wave types, being linked to acoustic, mechanical, thermal design, and other applications. The field of metamaterials has seen rapid and sustained increase in interest over the past 2 decades, with more than 16,000 scientific publications during 2019 alone. It is also natural to expect early applications to be reaching market at this time, given the elapsed period since their first discovery, and Robert has indicated projections of the market sizes. So in terms of applications, just to remind us, metamaterials have phenomenal potential in areas ranging from energy to ICT, defence and security, aerospace and healthcare. And a number of the case studies that will follow these talks will give greater insights into some of these areas. Of course, the UK has a strong position to exploit into these opportunities because of the academic research foundation that's been established through support by UKRI and others over the last 15 years. And this chart shows some of the recent active research grants supported by the Engineering and Physical Sciences Research Council, also indicating the breadth, if not the complete extent, of the academic community that can be harnessed and drive forward innovation. There are a number of large, greater than £1 million grants shown amongst these, and the grants show diversity from biology through to engineering and the different disciplines. While some of these projects demonstrate effective collaboration, even in the example of the Prosperity Partnership between the University of Exeter and Kinetic, a KTN review of metamaterials in the UK from 2015 identified the lack of coordination between R&D groups as a threat to the UK's progress. So today is very much about addressing this issue. Furthermore, current metamaterial projects funded by Innovate UK are relatively sparse. Just to name a couple of projects, Advanced Materials for Sodium-Ion Battery Anodes with Derigalia and Sonobex Acoustic Barriers. This imbalance demonstrates a need for a concerted effort to drive metamaterial science and innovation and push this impactful research area forward towards real industrial applications, alongside enhanced national coordination of the low technology readiness level work. There's been some effort to counter the above mentioned imbalance through the establishment of the Metamaterials Leadership Group that Robert mentioned and who I'm representing today, and other recent KTN events, including a showcase of emerging technology and academic and industrial metamaterials session at the Materials Research Exchange in London in February of this year. However, the need for a UK-wide intervention has been recognised to foster cross-sector collaboration for dual use across defence and civil applications, and a strategy to drive that forward. So this is important to consider the international perspective and the competitive state globally. Whilst a host of UK academics have offered world firsts in metamaterials, developing the science associated with sensing, photovoltaics, data storage, novel antennas, radar absorbers, reconfigurable photonics for communication, acoustic control, wireless power transfer, and many more, leading to university spin-outs such as Sonobex, Metasonics, and Metaboards, the UK risks falling behind the curve of metamaterials research and innovation. This slide shows a couple of examples. For example, Chinese government has invested in the development of the world's first large-scale metamaterial fabrication facility with the capacity to produce 100,000 square meters of metamaterial plates annually for projects in aerospace, communication, satellite and military applications. The US has also recognised the need for intervention. For example, the voice of the US National Advanced Material Manufacturing Community, M Foresight, highlighted actions necessary to ensure that metamaterials become more broadly adopted to address practical applications and deliver societal and economic value. Similar conclusions have come from UK bodies, including the UK's Advanced Materials Leadership Council, who, in working at the group position paper, recognised the strengths of the UK base that I've mentioned, including topics such as nanophotonics, 2D nanostructures and plasmonics that underpin photonic metamaterials, but highlighted that in metamaterials in general, the UK is lagging behind the US and Southeast Asia. Therefore, because of the significant and broad-ranging commercial opportunities and societal significance, alongside critical and enduring national security and defence need, there is a need to act differently and start acting now, hence the battle cry from Robert. In the face of strong global competition, we need to take a more organised approach as a nation, as postulated in this schematic. What is different in getting us to today, the beginning of a new era for metamaterials in the UK? It is that the conditions have been reached to attract government and investor support. This has been tested before in about 2013, but the conditions then were not ready. So it is that the UK metamaterials community has formed, and this is no small achievement given the technological and application diversity that I've highlighted. It is that this community has demonstrated a meaningful scale and intent, recognising the need and potential to cooperate in a coherent endeavour. And in addition, it's growing evidence of potential for businesses and new small businesses in particular to embrace and exploit this emergent and game-changing technology. So the first step is implementing support for the UK metamaterials community, and that's very much what today is about. This support comes in two parts, the first of which Robert is introducing and launching today. And moreover, it should be inspiring to us all that this launch is orchestrated together with a newly funded and partner network, which Anya will introduce next. The leaders of these two investments have identified common objectives and agree that they are targeting support for the same community and purpose and outcome. What is most inspiring is their coherent approach and common purpose, as highlighted here. The two endeavours team up under the banner Nurture, Develop, Exploit the UK metamaterials community. This approach is designed to magnify the impact of each network's objectives and activities, avoid duplication, optimise resources, leverage knowledge and practices, and prevent confusion in the community. Together, these interventions will help to bridge the valley of death, building from both sides for success. The Innovation Network will help the community spot investable propositions and showcase them to potential investors, to build vital evidence of the economic potential to inform further government strategy, policy and decision making, which, as I said, is timely and critical given the role of R&D in the comprehensive spending and integrated reviews and as they unfold. The EPSRC funded Metamaterials Network will build a platform for metamaterials researchers across higher education institutions, government agencies and industrial partners to communicate and collaborate and drive new innovation development. This will help maintain the UK's strong S&T foundation, address skills development, and ensure the funnel of opportunities is restocked. So how might a coherent community and an evidence-based economic argument relating to the opportunities lead to further strategic support? This slide gives an idea. To create appropriate R&D mass and momentum, large national investments can be a strategic signal to align the R&D ecosystem. Presently, these are funded schemes like Strategic Priorities Fund and Industrial Strategy Challenge Funds. So it will be encouraging to this assembled community to learn that EPSRC has requested an outlined big idea proposal of this calibre for metamaterials, and also further that MOD undertook an independent review earlier this year on the status of metamaterials in the UK. It is relevant to share that that review took a strongly dual-use perspective, and hence my participation in this. So we await the feedback from these further activities, but on behalf of the Metamaterials Leadership Group, I can say that with our membership spanning academia, industry and government, we are very pleased to be supporting you, our community, into this new era, and we should all be optimistic and empowered. So thank you very much for listening. And I'll now hand over to Anya to talk to us about the Metamaterials Network.
Thank you very much, Ian. So hello, everyone. As Ian said, I'm Anya Roding. I'm co-investigator on the EPSRC UK Metamaterials Network. Ian indicated that 2020 brought 2 UKI investments to the UK metamaterials community. So we are witnessing the launch of the KTN1 today, and I'm very grateful to Robert for inviting us to give you an outline also on the EPSRC funded initiative. Now, when I say us, I mean Professor Alistair Hibbins, who is the PI of this network, and myself. We are our home is the Centre for Metamaterial Research and Innovation, or short CMRI, at the University of Exeter. Al is Director of CMRI, and his day job is being Professor of Metamaterial Physics, and I'm co-director of the Centre and co-investigator on the network grant, with most of my time being dedicated to the management of these 2 investments to bring the community together. Now, a quick recap for those of you who weren't part of the journey so far. In November 2019, Al and I met with around 70 academics and industry representatives across the UK to consult on the idea of such a metamaterials network proposal, simply because, as Ian just said, the UK risks falling behind the curve of the metamaterials market internationally. So the community response was overwhelmingly positive. We utilized the energy committed by all the people who we liaised with to pull together this proposal, supported by around 45 letters of support, with more than 1.5 million of cash and in-kind commitment from 22 universities, 20 companies and governmental partners. So at the development stage, as you can see in this slide, we identified 7 initial special interest groups and 4 forums, which will form the core of the network at its very beginnings in March 2021. So there's active metamaterials, biophotonic applications. We're looking at flexible and conformable meta surfaces, and in particular, manufacturing and scale-up will be a key topic. Multifunctional and mechanical metamaterials is also core, as well as modeling and AI design, and wireless and microwave applications. In addition to the special interest groups, we also have 4 forums dedicated to early career researchers, to horizon scanning to see what's out there, what's coming up, how do we need to position ourselves. One in particular targeted at industry, just because industry really needs to feed into the academic community and identify the need and what's, what you need and what the challenges are that are lying ahead over the next decade to come. And then we'll also have a forum on outreach and education. Now, you can tell already it's quite a big, complex endeavor, and clearly driving all these activities across the range of the breadth of groups cannot be done just by 2 people. So we are very lucky to be supported by a really strong and dynamic leadership team of the special interest group and forum leads from a range of universities and the private sector businesses. This team will meet on 22nd of October for the very first time to set key priorities and plan initial activities in preparation of the official launch in March 21. And the key objectives we will be addressing are, first and foremost, community building. We really have to drive much stronger relationships across academia, and also between academia and industry and governmental agencies, to better understand what's needed and what's possible. We want to develop key documents such as roadmaps and white papers and reviews, just to enable much better access to the metamaterials landscape for all, in particular those who are not as familiar with it and who may be benefiting from exploiting this opportunity. We want to be an information hub, so we need a platform, a database for metamaterials expertise that you can access and find the right person for your challenge. In addition to that, it's about developing a talent pool. We want to support the next generation of scientists in the field and give them exposure to career pathways within, but also beyond academia. We want to raise awareness of the importance of metamaterials and their applications among industry, UKI and government, but also promoting it to the wider public, to non-expert audiences, to inspire and educate. And last but not least, we need to plan beyond 2024. We need to plan and the legacy for this EPSRC investment to keep the community going in the long run. So, right, as Ian indicated, there is clearly overlap between the KTN initiative that is launched today and the EPSRC network I introduced. And I'm very happy that we have really long-standing relationships between Exeter and the KTN to bring these two initiatives together over the next few months and act as one advocate for the community to nurture, develop, and exploit. And in addition to that, there's already a long-standing special interest group as part of the Acoustic Metamaterials Network. So the Acoustic Metamaterials Special Interest Group, we will be working with very closely. And if you're interested in that, you have a chance to approach their lead, Gianluca, today, because he will also speak later on about indoor sound management with metamaterials. And with that, that was a very quick glimpse on what's to come with the EPSRC UK Metamaterials Network. I would like to hand over to the first case study of the day, which is presented by Exeter's visiting associate, Dr. Mike Sloan from TCS, Technical Composite Systems. And I believe it's a native project on composite base plates for aerospace antennas. Enjoy. Thank you.
Anya, thanks very much. Yeah, we're very pleased to be a supporting signatory for the EPSRC network. So yeah, looking forward to the future there. I want to talk to you about a really successful project that completed early this year based on composite materials and metamaterials, led by Technical Composite Systems and supported by the NATEP programme. Okay, quick bit of introduction. The project partners, it was led by TCS. We are an SME in Devon, specialising in composite materials, manufacture and tooling. Supported in the project by the University of Exeter, that was Professor Hibbins, Roy Sambles and Cameron Gallagher at the Department of Physics. And Cobham Aerospace Connectivity provided us guidance on the communications hardware that were the core part of the hardware that we were working with. A little bit of background, if you look at the picture there, this is really just to illustrate the communication requirements for modern aircraft. It illustrates it really well, whether an aircraft's talking to other airborne vehicles, to ground installations, to satellites. There's a lot going on. There's a lot of antennas on manned aircraft and also UAVs with numerous sensors on board. Bit more detail, here's a 787. You can see the number of communication antennas for various frequency bands and operations, but effectively what you're doing is you're taking a nice aerodynamic tube and adding various fins and blades on the outside and turning it into a bit of a hedgehog. So there's an opportunity to improve that in one manner. Looking at the antenna in a little bit more detail, bottom right there, we've got sort of a VHF blade, and behind that quite a bulky SATCOM antenna. Now that's obviously sticking up in the airstream. It's got mass, it's quite bulky. One approach is to actually make that into a conformal antenna, which effectively sits within the aircraft and is flush with the aircraft skin. That's good news, but typically they're quite deep, they're quite bulky. So the premise for this project, our challenge, was to make conformal antennas smaller, less bulky, and lighter. There were two themes to the project. The first was composites, and the second was metamaterials. Now, as a material scientist, I'm going to indulge in composites for a little bit. We'll get onto metamaterials next. But effectively, my design challenge was to take an existing aerospace alloy, 6000 series, and replace that with a pre-preg. So we're talking about what are the stress levels, what are the statics, what are the dynamics, what are the mass that this unit has to hold and keep secure, what are the temperatures, the environmental lubricants, various anti-icing liquids you might see, and also electrical performance, and that's both desirable and undesirable. Here's a few pictures. So I'm going to talk about a base plate and a radome. The base plate is the tray, effectively the pie, and the radome is the lid. Bit more detail on those two. Typically, scale-wise, we're talking about, say, 300 millimeters diameter for the base plate, and the depth is entirely dependent on what frequency band you're working with. Our approach for the composite materials was just to technically map the requirements of the antenna system, then propose various pre-preg solutions, so pre-impregnated composites, add some functional materials to that for sort of lightning strike protection. We'll come on to that. Do a technical commercial review, and then design actually the composite layout, do some structural calculations to give us that confidence interval, design and make the tooling, design and make the parts, and then test them. So the most interesting test, and I'm going to come on to a video in a minute, is the lightning test that we did. And really this was a worst case scenario for our project. You know, what happens if our radome was to disappear or fail for some reason, maybe a bird strike or lightning strike 1, and we've got a new base plate on the aircraft surface, what happens if that's hit with a direct lightning strike? It could potentially happen. Is it going to survive? Is it going to break up into pieces? Aircraft are classified in terms of zones. So the worst bits, the nose, tips of the wings, tips of the tail. We're really interested in that purple zone because, as you can see, there's a lot of real estate there, and if we can pass the lightning requirements for the purple areas, then we can pick and choose where potentially these antennas could go on a large aircraft. Anything above that zone is a bonus. So what we did was we made a number of test articles with varying ply layups, varying degrees of lightning protection, and we tortured them for a day, which was a lot of fun. Now here's a series of stills from the test, and as you can see, it's quite dramatic. It all happens very quickly. The electrical impulse that goes through these materials is significant. Zone 1C is effectively a compound of these two curves. Different timescales there, just to note. But effectively, what you're doing is you're passing a very high current and/or voltage through this part and seeing what happens. Now, this is the video that isn't going to work, so I'm just going to duck out and play it through this medium. Here we go. It's about 16 seconds of video and about 15.5 seconds of intro. There's our base plate in the middle, mounted in a steel frame with a lightning pickup in the middle. There's a short alarm that comes up, and then everything happens with one flash straight after. There we go. So that's actually a 1C lightning strike zone on the brand new composite base plate. This is behind 2 layers of glass, but what we knew at this stage was it remained in 1 bit, which was a bonus. A significant bonus, I should add, and a lot of relieved engineers. Okay, there is that actual test article, post a 1C test, and we were extremely pleased with how that performed. So all of our design choices, our ply layups, there's a lot of interesting materials happening on the back of that, I should say. But we know for sure that the lightning pickup was in the center of that base plate, and it traveled either through or mostly across the surface of that base plate and was taken out to ground at the outer edges. So it's performed better than we originally hoped. Once we've done the lightning test, it then goes on to some more sort of aircraft qualification work known as the O160G, which is a whole load of sort of dynamic and static mechanical tests, shake, rattle and roll as they call it, various humidity cycling procedures, and some fluid susceptibility, so de-icing, fungus growth, that kind of thing. A massive result for our composite element of the project. Now it's to talk about where the metamaterials come in. So we've already made the base plate lighter through material substitution. Now we're going to make it smaller. So the challenge we proposed to the guys at Exeter was, can you make us something that allows us to shrink this base plate? Because it's taking up too much headspace in the aircraft, how can we make it smaller? And the challenge set to them was, can you give us a bandwidth, percentage bandwidth of greater than 50% with still an appreciable gain level, and a target depth of no greater than the wavelength divided by 12. Now, what does that mean? Okay, here are some slides I've hijacked from Dr. Cameron Gallagher at Exeter. But effectively, if you have an antenna on its own, it will radiate in multiple directions. You can significantly improve its directionality and its efficiency by putting it in front of an electrical conductor, a mirror. A sheet of metal does that fine. That's what the existing base plate did. But for optimal performance, you space it by its wavelength over 4. However, this is where metamaterials come in, and this is where the black magic happens, because it's over my head. I'm just a material scientist. If you have a specifically tuned, designed artificial magnetic conductor, you can significantly reduce that standoff. You can significantly reduce the depth of your base plate, and that's where we got interested. So, in theory, as it says there, as Cameron said, you could actually place the antenna directly on top of your ground plane. So have a very, very thin, negligible depth base plate, which is great news for the aircraft it's great news for the designers. How was that done? Well, obviously with the specifications that were given to the team at Exeter, they set about modelling and designing and simulating what's called a frequency selective surface. That's just a periodic structure of repeat copper patterns that are manufactured using conventional PCB techniques, layered up in appropriate design configuration. And then we take that frequency selective surface and we sandwich it with what's called a magnetodielectric. So effectively, you've got another composite material. This artificial magnetic conductor then goes in our base plate with the antenna. That again was all tested for full lightning and environmental tests. It passed with flying colours. I'm coming to the end now, so I've got a couple of slides really just to promote, we'll just talk about our project, but to promote collaborative R&D as a whole, because that's how my introduction to metamaterials happened, and that's how I imagine quite a large percentage of the audience will engage. The NATEP scheme was fantastic for us as an SME. It really supported us through. The highlights: bringing a team of engineers, antenna designers, tooling engineers and physicists together. That's great, doesn't usually happen. And doing something new. Anything novel is exciting. We passed the lightning test. That was a huge sigh of relief and a big achievement. But the funding regime that we had through NATEP gave us protected activity. So we had budgets, we had Gantt charts, we had resources allocated. We generated some very good IP in this project that we own between TCS and the University of Exeter. And it also gives me the opportunity to talk at events like this today. Difficulties, standard fare for any kind of project, keeping on track. 9 different designers with 9 different ideas, that kind of thing. Nothing out of the ordinary there. The huge benefit to TCS as a small SME is taking a concept idea and producing a test article that passes in a number of different arenas. That was great. And applying new skills to a new technical arena, physicists, engineers, we've got a lot to learn from each other. And demonstrating capability and programmatic control. We don't often get the chance of that as an SME against the tier 1s and the tier 2s. Coming to a close now, next steps. I'm very interested to talk to anybody in the audience who's interested in either the composites or the metamaterials that I've previously spoken about. It's at the higher end of the TRL level, but we need engagement from platform integrators, from end users to tune it to their application. We've done a brilliant technology demonstrator, but actually we need to now tune this for specific aircraft or applications. And what is exciting is because of the success of this project, we are rolling on to another project that is similar but different, where we're looking at shrinking these communication antenna even further on what I call a 2D level. So rather than going depth, we're sort of going X and Y. I'll leave my contact details up there for a few seconds. I'd be delighted to hear from anyone, even if it's a crazy idea, because that's how this all started. I went to Alistair with an idea at the KTN network 2 years ago in London. That forged a partnership. We're out the other side with a very successful project. So thank you to all the team members for this particular project. It was a lot of fun, a lot of hard work. Thanks to KTN. Best of luck with this network. I definitely will be part of it and contribute where I can. I think it's time for me to pass over to Panos. Thank you for your time and look forward to speaking to you either offline or in a networking event after this.
Thank you very much. So hello everyone. I am Panos Kosmas and I'm a co-founder of UK SME Metawise, and hopefully everybody can see this now. So I'm here to talk about what the company has been doing. I must say that I'm also an academic at King's College, a reader there, but I'm here to summarize the activities of Metawise. I have this presentation has been put together also by Themos Kalos and George Palikaras, who are also co-founders of the company. It has this very long title here, but there are some keywords: metamaterials, medical breakthroughs, radio wave technologies. We use microwave frequencies, but we prefer to use the radio wave term because microwave sometimes scares people when we talk about healthcare. They think of microwave ovens. And of course, point of care is another key term. We try to make affordable and portable devices. So let me try and use the laser. So I have quite a few slides. So I'm going to give you a high-level presentation. But first, I'll start with noting that MedDevice is now part of the larger Canadian company, Meta. And again, the name already suggests that metamaterials are somewhere used in this technology. And indeed, Meta is developing metamaterial technologies for different applications, not just healthcare. There are 3 related technology platforms: holography, lithography, and medical sensing. And the idea is to design and manufacture nano patterns on film, which are then developed for different applications. So I'll focus on the medical space, which is developed by the UK company MedDevice. And how are we using metamaterials in this space? Well, we have a patented technology that enables us to use metamaterials, metasurfaces essentially, to enhance penetration through the skin and increase the sensitivity of our sensing and imaging systems, as we will see later. The team here is, you see a photo of me, also George and Themos, who are technical leads. There are also Federico and Nadine here, who are in the business side of things. Our UK office is small. There are 3 engineering team members with PhDs, 2 of them PhDs, but of course we are part of Meta, which is a larger company, and we also exchange knowledge with them to develop these technologies. So again, a picture here that shows that what the metamaterial does. Basically, the idea is that it can help signals penetrate through the skin and also give us more sensitivity. And this platform has, we try to use it for different applications. I'm not going to go over this slide. We've already seen what metamaterials are. The concept is, of course, and what we always tell audience and investors is that these are artificial materials that we can use to for the benefit of our applications. So there are different applications that we've considered, but I'm going to look at 3 here, the ones that we are most active at the moment. It's non-invasive glucose sensitive, radio imaging, and magnetic resonance imaging. I should mention here that we have acquired funding by Innovate UK for all these 3 projects throughout the years. So we'd like to thank them for that. And this has helped us develop these projects. So I'm going to, of course, and of course, this is part of a larger vision that we are sharing with other healthcare companies. And it was already shown early through this tricorder system. So the idea is to have compact, portable point-of-care technologies that can give a lot of useful diagnostic information to doctors without necessarily having to go and have MRI or X-ray scans. And this is what we are after. So I'll show how, a brief summary of 3 different applications and how metamaterials are used in these applications. I'll start with non-invasive glucose sensing. So the project here is our project is called GlucoWise. And the final device that we have envisioned looks here. We're not here yet. We have a desktop prototype, lab prototype. And the basic principle is that we have an antenna sensor at millimeter wave frequency, around 40 gigahertz, and a metamaterial that is placed between the sensor and the skin to enhance penetration and sensitivity. We have been developing this sensor for a few years now, and we have managed to improve its accuracy, include auxiliary sensors, intelligent algorithms to translate the data. So there's a lot of R&D that is going on, obviously. But I'll focus, and we have done animal and human studies, preliminary, that have shown some interesting results that have been published on how we can estimate glucose changes non-invasively. Don't have time to go over all the details, but I'm just noting that we are now developing the 4th generation system, which focuses also both on algorithm and also on acquiring additional sensor information. How is metamaterial technology used in the system? So the basic concept is related, of course, to some of the properties that metamaterials have that have been discussed previously. So the idea is that they're placed between the skin and air, and they can achieve a 0 reflection or very little reflection and enhance the transmission through the skin and blood to then give us more sensitivity in our signals. And here's some experiments that we've done in the past that show that this is indeed the case. So the green line here, so here we've placed the metamaterial in the ears pig. This is our antenna sensor. So you see here how the transmission can be enhanced by the use of the metamaterial. We've done some experiments with humans, and again, we've observed transmission enhancement of the order of 200 to 150%. In radio wave imaging, the principle is different. We are trying to create an imaging device for stroke or breast cancer. And again, there's a lot of R&D behind this, but I'm just going to focus on what metamaterials can do for us. So we place the metamaterials between the antennas and the head in simulations or in some preliminary experiments that I'll show in the next slide. And we've managed to show that they can improve the sensitivity of the system. You see here two images from simulations, and there's a target here. These are with phantoms, of course, and you see how the metamaterial image has a lot less artifacts in the image. And we are the first to have shown this in simulations, but also in experiments that we've done. So this is a phantom with materials that resemble human tissue and something that could be a target, a stroke or a breast cancer, has contrast with the surrounding tissues. Of course, a simplified phantom, but we have shown that with the use of the metamaterial between the antennas and the phantom, we can actually detect the target. Whereas in case when we don't have the metamaterial, we actually have a false alarm. So again, this is the first time that this has been shown. And we are also working, of course, on breast cancer applications. The concept again being that we have an early system that can be placed in a GP and warn patients without having to have uncomfortable X-ray exams. In stroke imaging, there's also a need to have a device in an emergency vehicle to differentiate between strokes early enough. In MRI, the use of metamaterial is a bit different. Here, we're actually developing a device that is inspired by metamaterial. So again, I'm going to skim through the slides, but basically state that the need is to have quicker scans. For that, we have to have an increased SNR. And this is where we come in with a device that is, I'll show later its main design, but what it does is it can improve the quality of the SNR by 2 or 3 times, and that can improve the image quality or reduce the scan time. So we've done again some trials with MRI machines. This is what it looks like. It's an array of dipoles basically that is designed so that it can perform either at 1.5 Tesla or 3 Tesla. Here's an image that shows from the system shows the enhancement, the SNR enhancement that can be achieved through the system. And this leads to improvement in the image quality when the metasurface is on rather than when the metasurface is off. So I'll finish here because, again, as I mentioned, this is sort of a high-level summary, saying that, of course, we're not just developing the metamaterial technology. We start from that, and this is a unique value proposition for us, but of course, we also develop the actual sensors and devices that requires expertise in a lot of different areas. So that's all I wanted to say here. I thank you for listening, and I'm just gonna pass you now to the next speaker, who's Gianluca, and he will give you a summary in a different area of his activities in acoustics. So thank you.
Thanks, Panos, for passing me over. Hello, everyone. And so my role today is to tell you about acoustic metamaterials. So I am one of the founders of this startup, which is called Metasonics. And what we believe is that metamaterials give us an unprecedented control on sound and noise. And my topic today is indoor sound. So let me start my sound so that you can also hear some sound as we go along. And there we go. So I'll tell you something about acoustic metamaterials. You have heard a lot about metamaterials. I want to tell you just to leave you with some thoughts about the acoustic part of that. And then I'll focus on the problem, what Metasonics is doing, and then on a project which we recently got funded by UKRI. So what are acoustic metamaterials? So these are devices. If I use this definition, which says acoustic metamaterials are devices engineered to modify the sound that hits them or goes through them. If I stop there, I have just described musical instruments because a guitar is an object which has been shaped and geometrically shaped to affect the sound that is produced by strings, and the flute is an object where you press different buttons to change the sound. A Schroeder diffuser, if we go more complex, is an object you find in auditoriums to affect the reverberation, and so the sound that we perceive. And again, absorbing materials are everywhere, from not just in music studios, also on the side of cars. So there must be something more. So what I'm reporting here, you heard from Anya that I chair the Acoustic Metamaterial Special Interest Group of the Acoustic Network, which is another EPSRC funded initiative to study the innovation, in this case in acoustics. And we ran recently a survey on what is a metamaterial, a very simple question. And people came out with a few keywords. This is a word cloud, the result of that survey. And if I have talked about manipulation and waves, I didn't mention the other two, which are large here, which are elements and subwavelengths. So let me add something to my definition then. They are made of parts which are smaller than the wavelength, and they are called unit cells. And what you see here on the side are different types of unit cells, ranging from soda cans. This was the first acoustic metamaterial I've ever seen, to objects which are more complex, and in this case, 3D printed. But whatever is the shape, the University of Sussex and Bristol in 2017 found that you just need 16 predefined shapes to get most of the control that you might want to have. I should say whole at the time, but probably most of it is more appropriate. So if you can do this with predefined shapes, then building an acoustic metamaterials is like building an IKEA cabinet. You just need the blueprint. And so making the metamaterial becomes a design problem. And that is where Metasonics started. So to summarize, acoustic metamaterials can be used for sound manipulation. And so in sensors, in sending sound in objects, actually in sending just a spot of sound to people that can follow them. But when you talk to people and you talk to them, what do you imagine their role is? They all mention noise cancellation. So metamaterials, as we heard earlier, is a technology which is transitioning from academia to commercial use very quickly. And that's why we have so many startups. And these two applications for us at Metasonics are called Sonoblind and Metasonics, with a CS instead of XX. And we have, as a company, an exclusive commercialization rights on 4 patents related to this arena. So what is the problem I want to share with you today? So we have been through summer, it's almost over here in Brighton. Imagine a warm summer day with your windows open, and suddenly a noise outside. That can be a plane, that can be a garbage truck, can be a car passing by. And suddenly you don't want to keep your windows open anymore. But at the same time, you want, because that is your choice. You want to control on what's happening outside. This small story summarizes a situation which is common to 40% of the population in Europe, which are exposed at home or at work, at noise levels which are not high enough to create heart attacks risks, but are still sufficient to cause annoyance and stress. The World Health Organization has estimated that more than 1 million of days are lost to stress caused by noise. So then, if we can control that indoor, then this improves our life. And so this is a problem which has been common to many different applications. And you heard from Robert that acoustic metamaterials position themselves mostly in the building arena. Not just that, but most of them. And I have a citation here from a document from the UK Acoustic and Noise Consultants Association, which is dated January 2020, or I should say now pre-pandemic. And they were talking about open offices or schools. So imagine you are in an open office, if we ever get there again, and there is your best mate talking on the phone all the time. Again, these are situations which you might have experienced yourself. And then if you want to scale up a blind for sound. So a solution where you have sound and fresh air, and you pull down something and suddenly you don't have the sound which was annoying anymore. You just have the sounds that you want, and that is a key important bit. So you can imagine that for air conditioning. So like a grid, like the ones that are in top of, on the top of all other rooms, or like a trickle vent, like that, those which happens at the bottom many windows in the UK. Or again, you can imagine in open offices, and you can imagine panels which you can slide down as you need, or even pods, where however, there is still air through and you don't feel enclosed and blocked inside. Now, I was telling about selecting the noises and the sounds that you want. And this is a performance of a metamaterial that we presented in February 2020 at the Metamaterial Exchange organized by KTN, which as we heard, and that's why we are today so on the forefront of these technologies. And you can see that this reduces sound at this range of frequencies and above, but lets this frequency through. So if you have an alarm or a mobile phone ring, this will go through. And so you can still be able to communicate certain messages, but not others. So in how this positions with existing technologies? Well, the winning bit of this technology is our unique proposition is the higher airflow, because you can obviously box everything in a double glazed system, or put in strong acoustic absorbent panels, or even you can buy a very high-end acoustic window, or you can have trickle vents, which again are very more powerful. So sonoblind is not so strong, it doesn't get to 60 dB. So it's not for when again there is a risk to health, but it is for places where you want air and control sound at the same time. So this was us before the pandemic. And then the pandemic arrived, and we, like many other SMEs, started thinking about the future, about the world after. Now, we are already talking about a new peak. We're talking about probably COVID-19 staying with us forever, or maybe as long as we get a vaccine. So this made us think about hospitals and staff exposed to working in intensive cares and exposed to noise. So these are two figures which are actually measurements made before and after, before the pandemic. So when it was not so bad as it is now. So these are the recommended values, and these are the values that you measure. But let me just give you an example of what's the sound in an intensive care unit on the bed of a patient. And what you're hearing is a bit of speech. And then you're hearing alarms. And then you're hearing different sounds coming from different systems. Now, these sounds are proven to impact the health of the patient and the recovery time, but more importantly, perhaps, they are proven to impact on the well-being of staff. So, the pandemic transformed a lot of hospital wards into intensive care ones. And if you look at the guidelines to do that, you find that there is actually a limit in terms of noise emission that a ventilator should have to be used for treating COVID. And if you imagine that you just have 10 ventilators in a room, which is common in a COVID ward, then the numbers go up to a level which is similar to an high trafficked road. And what is the sound like? So in terms of frequency, it has some spikes, which are the frequencies of the alarms, and then there is a broadband noise which goes all around. Now, the orange line that you see here filters that according to what we actually perceive. So we are not so good at perceiving low frequency noises, but we are very annoyed by objects in this range. That is why the technology that we have been developing, thanks to a feasibility study funded by UKRI, might give us a quick solution for this type of problem. So let me show you some of the examples. This is a panel which is closed on one side and has a small, has a thin film on the front to allow it to be cleaned. It blocks 20 dBs over 3 octaves. and it weighs 1 meter squared of object, which is this big, weighs 9 kilos. So it's so light that people can move it around and staff can move it around without training. But the challenge, obviously, as I said at the start, is to design a panel which also allows air through. And so at the moment, we have designed this type of panel, which is focused on alarms. And so we imagine it around noisy equipment, mounted, again, like a patchwork system. And this is even lighter, and with 1 inch of thickness, it has the performance of 4 inches of wood. So to summarize my point of view, metamaterials nowadays, making them is a design challenge. And as a startup, we see different companies starting to use the term, and we heard earlier that there are countries outside the UK which are much more advanced in terms of product development and investment. And so, but we see loudspeakers, for instance, nowadays that are, so KEF, which is a UK and China-based company, came out with the first loudspeaker which mounts a metamaterial at the back. So there is an increasing awareness of what you can do with metamaterials, but it's still, metamaterials is still an exotic word. And so for a startup, it's still difficult to get investment. So the valley of death is still long. So this network is very, very timely. And so as a founder of a startup, I really hope that this allows us to contribute to the UK PLC and in general to see a growth or more entrepreneurs which take this exciting technology to applications which are life-changing for many. So a quick look to the program. This finishes my part, and I think after me there is James Johnston will tell us about his experience with metamaterials. Thanks again, and if you want to get in touch, please do.
Thank you, Gianluca. That was excellent. Thank you very much. I know we've spoken on a couple of occasions. I'm James Johnston. I'm the Chief Operating Officer for a small company called Advanced Material Development. We have started about 3 years ago, and it was for the exploitation of 2D nanomaterials. So I'm coming from the perspective really of looking at scale up and the manufacturing side. My previous experiences within the KTN, I was formerly employed there, and was looking at graphene and also energy harvesting, and also I was part of the micro and nano manufacturing initiative way back in the DTI. So there's a lot of, so my interest in manufacturing has been around for a great many years. So just a quick introduction to AMD. AMD is exploiting technology from the quantum materials group within Sussex University, and we also have interactions with Surrey University on photonic metamaterials. So we're been operating quietly in the background, developing our inks and materials to apply to this field. So what I'd like to talk to today, and of course we're open very much to collaboration with many different partners. We're kind of moving out of our experimental phase into the collaboration phase, where we'd like to develop, we'd like to push some of our technologies to higher TRLs or manufacturing readiness levels in order to commercialize some of these innovations. So I'm looking at it from the perspective really of wanting to scale a metamaterial or a meta surface. So we're assuming here that we've created something and we have access to the IP. There's lots of that. We've identified some applications in mind, and we have some end clients in mind that we want to work with. And we've definitely seen the opportunity to commercialize and make money. So scaling and integration takes time and effort and money and lots of it. So this is an exercise that people should undertake with both their eyes open. So if we want to scale, then we might want to consider certain commercial questions before we embark on that road. So we're assuming, of course, that the innovation may be a platform technology. It may be applicable to many types of scenario. So then we have to think about what are the deployment modalities and the form factors. This will give a lot of insight into the possible manufacturing processes that we're likely to use. And we also need to consider what the likely volume is and the user demand. So constructing a value proposition and discussing that with a client is very, very important. There's nothing like presenting something to a client and then turn around and saying, well, actually the incumbent's much cheaper, go away and think again. So you have to be very careful about what you're, about the pitch that you're making. And sometimes in our experience, it's often about what we kind of call the meta business case. So it's looking at what your client's value proposition is to their clients. So that is obviously something that's very, very important. It's not just pitching and understanding the value proposition to your client, but their clients as well. And then of course, you're looking at costs, prices and competition and different scaling models. You might need to consider the amount of capital investment that's required if you need to scale to a certain level, to deploy to a certain level. And that will, of course, require investment both in the public and private sense. So there could be several different manufacturing strategies from taking a metamaterial or a meta surface into the market. So you could mix and match discrete and continuous production methods and scales. And you really have to know the actual engineering limits and the potential material defects that happen at that process. So all of these are finite, and we have a typical top-down approach where we're making macro structures from centimeters or millimeters. We might use a 3D additive technique, but we also come from the opposite ends of the length scale, from the nano and meso. So we're using a lot of self-assembly mechanisms. And that's kind of, the manufacturing process may well be governed by the speed of diffusion of species or the ordering that you can induce within these structures, and then looking at curing or drying or other processes. So the key really is to look at the value proposition, identify industrially relevant routes and organizations, and realizing the point at which you might realize the value. There might be a natural point where you say, right, okay, we've developed a manufacturing process, we've validated that. We don't want to do that as an entity. We want to pass that to somebody else. That's completely fine. And that would be an acceptable exit for a license or something, or a spin out or something like that. So just consider, when we're trying to commercialize something or make something into a product, that multiple fabrication steps adds cost and complexity. So the key here is really to design for simplicity. I've seen this lots of times. So what you don't want to be is beholden to one particular process that takes forever. You want things to be relatively smooth. So if we're scaling metamaterials from a kind of a scale-up perspective, we obviously have base materials. So we're into the world of chemistry, we're into the world of ceramics and polymers. Can you access scale-up processes that are relevant to making sure that you can roll this out on maybe a multi-kilogram basis? Or if you're looking at sensor, maybe you can kind of get away with not using so much. You will probably have to develop, you might have to develop certain types of composite inks that could be used in an additive manufacturing method, or so you have to look at the rheology, things like that, and to match those with the printing process or the additive manufacturing process that you're looking at. And there's all sorts of manufacturing processes that can be used to make metastructures. So you may print these things, you may have to sinter or extrude them, or you're making a foam, or you're making an aerogel, or you're making like a sol gel synthesis, which then you have to supercritically dry. So all of these have their individual characteristics in terms of their processing windows. And you also have to bear in mind some of the curing times for some of these. So some of the 3D additive manufacturing techniques are quite slow relatively to the amount of volume that you might need in order to get a product into the market. So you might need to look at some of developing the equipment that's that's being used for the purposes of manufacturing these metastructures and metamaterials. And also, when you're looking at larger volume or scale up, you might have issues in mass transport or energy transport. So looking at the homogeneity of a layer or structure at the edges compared with the middle. So there's also, when you enter this phase, you're looking at modeling of processes. So there's a lot of work that goes on in terms of, say, injection molding or printing, to looking at the way that the material flows inside a manufacturing process. So from a metasurface perspective, we may want to choose solution process routes or vacuum process routes. Both have advantages or disadvantages, and we also have to consider within the workflow whether there's compatibility issues. No good if you need to expose a device or a component to a high temperature process when it will melt. So you might be looking at XY patterning or Z layer patterning of devices, and you want to identify, when you're designing things, gaps in the manufacturing process that you need to address. And those gaps might present you with significant extra costs, because you might have to work with the instrument or the equipment manufacturers in order to develop the process that you need to be able to exploit this into high volume or into high volume. So there's a large range of processes which are available. We haven't spoken much about that. So from 2D printing, vacuum deposition, there's exciting developments in nano imprinting, etching, mask evaporation, laser micromachining. There's a galaxy of techniques that can be used. There's a big community out there in Europe and in the UK who are very much at the forefront of precision engineering. And we can take that through to some really quite exciting manufacturing techniques. So kind of the latest things for nano patterning, looking at UV interference lithography or super resolution SLA printing. This is the kind of nanoscribe tools, or looking at nano imprint if you're making a roll-to-roll type device. And then you're looking at very fine layers. You might want to do CVD. Of course, that's useful for some of the graphing work. Some of the ALD, which is used for digital patterning of graded surfaces. And also you might want to consider multi-beam laser manufacturing techniques, where you can introduce parallelism into the manufacturing process. But also we have to consider some of the finishing steps. This is sometimes very much overlooked. Certainly, if you have a metamaterial, you might have to make a component, you will have to package that, you might have to present interconnects, and all of those require expertise, which can be the preserve more of the microelectronics community or the photonics community. So reaching out into those partnerships is very important, because a company doesn't have all the necessary skills to do that. So it's important to do that. And then further integration into other electronic subsystems, as we heard before. One of the other bits of commercialization that's very important, testing, trials and confirmation. We heard obviously that if you're in the aerospace industry, certification is very, very important. This all takes time, money and effort, and access to the right mechanisms for funding is therefore very important. So you have several options if you're sitting, say, in an academic sense, and you've developed something. So you may wish to start a new company, and you can fund that through equity investments, and you might be able to de-risk that through the use of grants. Or you might build upon existing ventures that help you, or consultancies that can develop your metamaterial into a product. So you need to seek some partners, make sure that you have adequately protected your intellectual property. But then really the human aspect is what kind of level of commitment as a person sitting where they are you willing to take? What kind of risks are you willing to take to commercialize some of these innovations? And some of this may relate to the way that you choose about your career. And are you in it for the long haul, or do you just want to package something up, license it, move it to somewhere else, and then move on to the next material innovation? Those kind of decisions have to be made. So when you're looking for a partner, you're looking at the capability and the competence of them. Can you physically access the equipment? Is it difficult? How easy is it to get funding to be able to do trials? Lead times for materials. sometimes if you're upscaling, you might need a lot of material, and this might need to be made, and so therefore it might take weeks or months to get to a point of upscaling trial. And you may of course need to modify the equipment that you are using. So there are public funding mechanisms for funding metamaterials exploitation. There's the classic, of course, UKRI Innovate. There are the Industrial Challenge Fund themes, so things like Made Smarter or Faraday. The SMART Awards have been around for a very long time, although they're quite difficult to win. Of course, DSTL in the DASA, the Emerging Technologies and Rapid Impact, and some of the theme calls. There's European Union. I would say that's not a closed book, and a lot of the manufacturing expertise resides in Europe, especially in places like Germany, Belgium, Finland, and Sweden, where a lot of investment has gone into the micro and nano manufacturing equipment. So connecting with those is very important. So there are still some schemes that are open, certainly Eurostars and things like Penta in Eureka. And I think we wait to hear clarification from the UK government about participation, UK participation in the European Union. And there's also a small amount of money in the digital innovation hubs in the Cascades. So for scale up and infrastructure, we're looking, so the government has already made huge investments in capital infrastructure, things like the high value manufacturing catapult, which I was part of. There's also things like the compound semiconductor catapult. There's also centres of excellence for photonics up in Scotland. Also the Royce Institute, if you look on their website, there's lots of equipment to develop things, and other major universities as been described. So places like Nottingham, Oxford and Cambridge. And there's also private consultancies that will help you develop and do some of the design work to make these into products. So really, AMD's involvement in metamaterials and meta surfaces, as I said before, we've been involved in developing novel 2D material inks and formulations. Graphene has been touted as a very good general broadband absorber for a wide range of frequencies. And you can modify these films to make all sorts of weird and wonderful structures that interact quite very closely with electromagnetic radiation. So we can also, as part of what we're doing, it's early stages yet, we have access to technology, and we will be developing in the coming months an exciting project, which I can't tell you much about at the moment, where we're using self-assembled monodispersed polymers to make interesting photonic crystals, which can act as sensors. So we can show that they change their color with stretching it, or they also change color with exposure to temperature. So we're quite excited to be part of those initiatives to develop those materials and end applications. So I just wanted to say thank you very much for listening to this. My contact details are there, and I would like to hand over to Sajjad Haq, who is from Kinetic.
Okay, good morning, everybody. So yeah, I'm Sajjad from Kinetic, and I'm going to be sharing some thoughts about the exploitation of metamaterials. From an end user viewpoint, a fantastic title, which I need to thank Robert Quashie with. On my next slide, I will be a little bit annoying, and I will be mentioning my next slide every time because of the way that I'm actually operating here. But I will give an introduction to Kinetic for those who aren't familiar, say a little bit about some of the technologies we've been developing, discuss some of the pitfalls, and hopefully give some hints and tips on some of the ways that we found around them, not in any great detail, and then just highlight again, not in any great detail, a recent technology that we've been developing with our supply chain, and then provide some information on how everyone may wish to work with us. My next slide So Kinetic, for those who don't know, was formed in 2001 when MOD split its DERA Defense and Evaluation Research Agency into two. So it split into DSTL and what is now Kinetic. Kinetic became launched on the stock market in 2006, I believe. So on the left-hand side, you can see that there's a whole range of what we call themes or capabilities that we work in. I'm not going to go through all of them, but the top left one is effectively advanced materials in manufacturing. And that essentially highlights the importance that we take in terms of manufacturing processes and materials. And on the right-hand side shows some of the sectors that we work in. And they are very, very broad. We're no longer solely operating in the defense sphere. So it's defense and civil applications and across the board. Next slide. So we set up about a couple of years ago, we took a conscious decision within the business, and I was part of that discussion, to set up our Advanced Services and Products division, which effectively is an incubator hub that develops technologies from a low TRL all the way through to exploitation and to product, and to do that quickly. Now, we can't do that on our own, and consequently we've set up a very large ecosystem and partners that we work with and a supply chain. And again, hopefully that will become evident as we go through this presentation. On my next slide, materials is very important, as I've already said. We do undertake the low TRL R&D. We undertake the product development. We also provide advice and consultancy, and we've got some very well-equipped laboratories, manufacturing facilities, which allow us to do measurements and analysis as well. So some of the areas that we're involved in terms of materials include, well, 2D materials and graphene, since we were just talking about that, composite materials, battery technologies, armor materials, and it's effectively, it is across the board. And that does reflect the diverse nature of the business and of the markets and the sectors that we're involved in. Okay, on my next slide. So I've asked the question there, are metamaterials any different from any other materials? Being involved in the materials space, I thought I'd just ask that question. I'm not going to answer it, but certainly, I guess we've already heard today about the diversity of metamaterials. Professor Ian Youngs and Robert have spoken about it to some degree. And if you look at the literature, even the very, very early stages of metamaterials, you get these acronyms like EBGs and FSS and RSS and AMCs, and they go on and on and on. And that starts hinting at, I guess, the amount of work and the diversity in these materials. And then when you start adding in the sort of potential areas where you can actually use them, for example, we've had a great presentation from Gianluca on the acoustic side. There's the RF, there's optics, mechanical, structural, thermal applications of these materials. And then you start looking at all the different sectors in multiple markets. Then effectively what you've got there is a great big mess. And that creates a big problem and a headache for me. Because how do you start mapping all of that and making sense of it? So that, in a sense, is one of the weaknesses of metamaterials. They're so broad, they're so diverse, that it needs a lot of navigation through all of that to get it right. However, the strength, of course, is that it creates a tremendous opportunity. It's a playground for people who are willing to engage in it and actually start pulling out and assessing what can actually really add that societal benefit. Okay. Just to illustrate that, on my next slide, I've got some products. And another point I'm going to make out on this slide here is the fact that these are some products. To some degree or other, they use metamaterials. However, what you will notice from this slide, and I'm not going to go through all of these applications, is that where is the material in there? In only maybe 1 or 2 cases, there's a standalone material which we would sell as a product. The majority of what happens is, and I think James elegantly actually alluded to this in his presentation, it's about that integration of the materials. It's about the rest of the system that's absolutely key. On my next slide, a few more examples of areas that we have an interest in and where we've got active programs. So on the right-hand side of this particular slide, you know, what we consider to be really important is things like the IoT technologies, wireless data power transmission. On the next slide, please, is our areas that we're working in terms of acoustic metamaterials. And again, you'll see on this set of slides the fact that in order for us to be able to do this, they need to be able to have those R&D programs and the partnerships, even at the early stages. On the next slide, again, I think James alluded to this, chem biosensors, energy harvesting, imaging, all of these things are very, very important. Okay, so on to my next slide. So clearly that shows that the diversity in metamaterials. So how do you deal with it? How can you make sense of it? So a few, I guess just a few comments from me. What do we do? There's a number of different things, and I don't have enough time clearly to discuss all of that today, but I guess one of the things that potentially you could do is hedge your bets. We don't necessarily do that. I'm not suggesting you do, but I certainly know a lot of organizations that do tend to do that. But clearly what is important is understanding when you need to make an intervention. That's absolutely key. And on your right-hand side is a schematic of the hype curve. So using that as an example, where would you need to start to partner? Do you do that at the very start of the technology? Do you do it to try and overcome that trough of disillusionment, as it's nicely quoted? Or do you do it actually when things are a little bit more stable? And those are some of the decisions that I have to take on a daily basis, along with, you know, who do you partner with to do that? Do you invest in those areas? And of course, they're all different for each application. And that's what becomes complex when you're basically running a portfolio of materials and a portfolio of technologies. What you need to do, of course, is understand your landscape. You need to understand that ecosystem, who you can work with. And very importantly, what a business needs to understand, what is their risk profile? Do you want to be entrepreneurial? Do you actually want to stick your neck above the parapet? And, you know, when it's at the low TRL levels, is that when you want to get involved in it? And there's different schools of thought. And again, we will tailor our approach to that depending on the technology, depending on what's needed at the time. So we will work across all of those. You know, we will work with academias, we will work with SMEs, we will work with other end users, because that is our ecosystem that we have to work with and get right. Okay. On the next slide, there's a few key messages here. Basically, as I've already said, there's a limited market for the materials. They need to realize the value as part of a larger system. And that isn't easy at all. Okay. To understand the role of the materials and of the wider system, that does require close collaboration and co-development. And that's absolutely key to the way that we operate. And it's also important to understand, and particularly this is very, very difficult when we talk to a number of academics, when we talk to a number of new startups, that the largest costs are not necessarily the materials themselves. or that low TRL development. And that very frequently gives rise to where is the value being added for a particular technology. Okay? Who or what share of the IP who gets what, basically. Okay, and a lot of the time the expectations are not realistic. So effectively, I guess what I'm saying is that the exploitation, the barriers to that are only part technical. However, as I've said on this slide, what do metamaterials give you? They will give you that design freedom that will, if managed correctly, lead to improved products across multiple sectors. And we're beginning to see that. Okay, on my next slide. Okay, this is a relatively recent example. There's a number of examples that I could have selected, but this is an interesting example which highlights a lot of the things that I've just quickly mentioned. So this is a partnership between a company, a relatively new startup called Isotropic Systems Limited, who are in the business of developing satellite terminals. So we worked with these guys to develop a materials-based technology so that they could attack several different markets and produce technologies such as, on the left-hand side, is effectively a consumer broadband terminal. It's very, very low cost because it's the requirement for that is based upon the fact that something like 53% of the world is actually not connected. Okay? And the majority of that, something like 75% of that, is actually within 20 countries. So where there's, for example, in the third world, where they cannot receive the signals, there is an absolute desire and need to have technology that could improve their lives. The requirement there was to have a very, very low cost technology, because obviously the affordability issues were there. And then that meant from the bottom up, from the early design stages, we had to factor in the costs in terms of scale up and manufacture and get that right. On your right hand side is another future technology based upon some of the isotropics work and kinetic material based studies on satellite on the move for aircraft. We already had a great presentation by Mike on aircraft antennas, and this is essentially a different solution to a similar problem. In this instance, the market is executive jets. What this illustrates, and having seen from the very early stages of this through to the fruition of this, there's a few interesting things that I'd like to point out. Firstly, the actual inspiration for this technology was as a result of some real work that was done at Queen Mary University under the auspices of Professor Yang Hao, who did a lot of innovative work in the area of transformational modeling and materials design. But how that's transitioned into something which is actually real and usable is very, very interesting as a case study. I won't go into it in great detail, and hopefully I will get an opportunity to do that, but it actually maintains very little resemblance to what started out. However, without that initial nucleus, without that initial starting point, where we are today may not have happened. In addition, what we needed to do very, very rapidly, and is in the space of between 1 to 2 years, is set up a supply chain to be able to produce, manufacture, test, evaluate, and qualify these materials for some of the very rugged specifications at the very low cost that were necessary. And That's something Kinetic is expert at doing, and it's only possible because we do have that very large ecosystem, and we have that supply chain in place, but we needed to add other actors into that. And that's absolutely critical to being able to deliver this. On the next slide, okay, I guess this is quite generic, but it will perhaps help anybody out there who wishes to work with Kinetic to inspire them to either work with us in terms of accessing routes to market, developing exploitation paths, look at using our supply chain or setting up a new supply chain if necessary, and basically developing the value proposition. And again, that was alluded to by James earlier. We do have funding. We also fund organizations, SMEs. We co-develop, and effectively we operate with a very flexible business model. And that can be spinning in technologies, it can be spinning out technologies. As I said, it can be co-development, it could be co-funding, it could be joint ventures, it could be licensing. We do all of that on a daily basis because we have to. And that's absolutely pertinent to Metamaterials because, as I keep coming back to, because of their diversity in their fundamental architecture, but also in the diversity of applications and the market sectors. Okay, and my last slide is just a thanks to everyone, in particular to KTN, Robert, Tatiana, and Poonam, who've put this event together. I shall hand over now to John.
I'm going to say good afternoon, everybody, because it's about that time now. So I'm John Bound. I actually work for KTN. I'm in the innovation and design team as a knowledge transfer manager. 15 years ago, I was head of innovation development at the Royal College of Art in London. And one of our professors was very keen to connect with the materials community. At the same time, the then CEO of the Institute of Materials, Minerals and Mining, Bernie Rickinson, was very keen to connect with designers, product designers, architects and so forth. And a happy marriage formed. And Robert Kwashi, who's on this call, was the kind of person who brought the two together and obtained some funding initially from DTI to make this work. And really, as it says there, it's a unique partnership connecting material science and design communities to stimulate innovation. So I was involved in this 15 years ago as part of my then role at the RCA, and I'm now working at this part of my activity at the KTN. And really the idea originally was to form a partnership or a network of like-minded organizations. And you can see down there, we've got the Royal College of Art, KTN, the Materials Discovery at UCL, the Crafts Council, and the Institute of Engineering Designers. So quite a powerful combination of organizations, all coming at this topic from the different directions. And so how could we bridge, if you like, the valley of death between the materials science community that's developing new materials and the design community, which is very focused on application. And the thinking was that if we could encourage scientists to think more about or get more involved with application and designers to be involved earlier on in the development of materials, that would be a helpful thing for both stimulating commercial innovation, but also growing the economy. And just to indicate the kind of territory we're in, I guess in this diagram, we're coming in around about aerospace, and we've done quite a bit of work with aircraft interiors and so forth, right through medical and consumer products, and through to, I suppose, we probably fall short of fine art and sculpture, although we've ventured into that a little bit, but those are the fashion is in their products, packaging. So everything from material selection, manufacture, cost, through to style and culture is the kind of territory that where we engage
from the design side with materials and vice versa. Just to give you a flavour of the activities, we've been going for 15 years, so there's an awful lot of activities. If you go onto our website, we've got an archive there. So this is an indication of the whole range of things. Our very first event was on green construction. We're still very much focused on sustainability and circular economy, but along the way, we've done a lot of other projects. And very much the focus is on bringing people together from the different communities and forming a common language. And here, top left, we've got a workshop on impact protection when we had one of the senior materials developers at Nike. Top right is a much more recent piece of work on future banknote security. Bottom left is Kenneth Grange, the designer of the 125 train, and many, many iconic designs in conversation with Hugh Aldersley-Williams who's got a physics background, I think. Bottom right there, we've got two young women involved, one working for Jaguar Land Rover, the other working for a leading design agency working on aircraft. So very much quite a bit of strength there in transport. And in the middle at the bottom is an indication of we haven't just been a talking shop, there's been a lot of very hands-on, possibly without full health and safety in this particular instance, but this was an afternoon at the Royal College of Art some years ago when we called it the materials experiments, and it was in a session in the spirit of the Lunar Society of Birmingham, for those who know about that. So very much working with materials in all kinds of ways as a learning experience. And this is, we had a fantastic visit to the 3M Innovation Centre at Bracknell, invited by Ben Watson, who's Global Innovation Leader at 3M, bottom left, who's now one of our advisors. So this was a great day when we brought together really, both students, design practitioners, material scientists, all in the spirit of experimentation and adventure. The next few slides are some of the, if you like, the educational activities we've worked on. This was a wonderful summer school some years ago, focused on bicycle design, which is a great thing for students. We had about 40 students from all over the country. Bottom right there, we've got Mike Burrows, who was the designer of Chris Boardman's winning bikes, and it was great to have him there. Bottom left, I think we started the session at the materials event at the House of Lords. And up at the top there, you can see there's Robert wearing a very early prototype of an extremely lightweight bicycle lock, and two of the people involved with this went on to do a lot more work on that area and have got crowdfunding projects running. So that wasn't the real intention, it was more to bring the communities together, but it did have some commercial spin out. We regularly provide talks at an event called New Designers, when graduating designers from around the country display their final projects and are seeking either job opportunities or to promote their innovations. I think about 3,000 exhibitors take part in this. Is a big show at the Business Design Centre in London, which is also KTN's office, London office. And here you can see where the materials team, the KTN materials team, giving a talk on graphene and other 2D materials, and then networking with them afterwards in our annual materials clinic. At the top there, you can see our colleague, Brian McCarthy. Brian was really active in this activity over many years and was, in fact, the person who was working on this particular, the Metamaterials Innovation Network, until he sadly passed away a few months ago. But his spirit is very much with us as we go forward. And just to show that it's a two-way collaboration. Here's a bunch of young material scientists from the University College London Materials Discovery with their professor. And what we did was invite them along to go to this show, meet their peers who are designers, and to give some feedback on what they learned from that. And that was a fantastic activity. And we've got some video interviews and so forth with them on our website. Going the other way round, we've brought young designers to the Material MRE 18, this was, I think. So we had a 24-hour challenge. Several teams of designers were asked to, or invited to go around the show and see what they could find that would stimulate a design project. And we divided them into teams. I think there was sustainability, healthcare, and energy. And this particular team focused on healthcare and picked up on, for instance, hydrogel, some sterile dressings and so forth. And 24 hours later, they were able to present, bottom right there, some exciting design solutions and take part in a discussion with quite a substantial audience from industry. So that's really just to demonstrate that this is very much not just a talking shop, but it's very much a practical project where we're trying to bring real change together. Another way we've done this is through competitions. This was a competition which with our colleagues at the Institute of Materials, Minerals and Mining, and the resulting, the winning project was a water purification system for use in developing countries. I was quite involved for a couple of years in an EU project called InnoMatNet, which was essentially attempting to build a network across Europe of material science and designers. And bottom right there, you can see a summer school that we organized with young designers and material scientists from across Europe who came to London for a few days. And up top is a best practice guide, which I put together of case studies of global best practice, bringing materials technology and design together to improve innovation. I'll now just run through very quickly some projects where we've worked with industry and government agencies, in this case, the prison service. So this was where we were trying to stimulate new thinking around procurement, but particularly relating to prison mattresses. 40,000 of those go into landfill every year. And we ran a very exciting project looking at the opportunities to improve that product, both to reduce the impact on the environment, but also to make the prisoners and the staff's life a bit easier. I was involved with this project. This was about a 6-month research project at the big request of the Home Office, but channeled through the Design Council. And this was looking to reduce crimes based using beer glasses, wine glasses, and so forth. So as you can see there, a lot of research behind this, a fantastic workshop when we brought together the police, surgeons, designers, branding people from the major drinks companies, and looking at various ways forward. And this led on to some work with BSI on standards. One major manufacturer did change their products as a result, and it was very much to stimulate new thinking around that particular issue. We've worked quite a lot with Jaguar Land Rover to stimulate their thinking on the circular economy and vehicle end of life. Bottom right there, you can see a project where we challenged young designers and material scientists to take car doors apart and really have a good think about how those parts could be better designed in order to make disassembly more feasible and so forth. And part of this was also visits to waste production centres and so forth. So it was very much a kind of hearts and minds project. Similarly, working with Arup on building facades and thinking about how those could be improved to with the circular economy agenda. And mentioned earlier the work we've done for a major banking institution on banknote security. And this is where we've now refined the process that we've been using here. We call it whiteboard innovation. And it's a mixture of bringing together people from science, art, design, manufacture, and end users and retailers, setting the scene. Our hands-on activity is incredibly important. So here we are testing and working with banknotes, and then idea stimulation and sessions and reports and so forth. So that's something that we've been refining for the last few years, and is quite an established process that we've now got. Just to show that we've managed to keep going during the lockdown, this was a few weeks ago when we ran a session on sustainability and entrepreneurship for new designers. And you can see there Sally Backen and Ajay from our team. We're all wearing the May t-shirts. And just to conclude, this is a bunch of us. It's a very friendly setup, and we're here to help, really. Communicating across the design communities, whether it's product design, architecture, whatever, and through into science communities as well. So I think that's about it from me. Contact details are over there. I'm John Bound. You'll find my details, I think, on the system. So I'm now going to hand over to Robert, I think, to wrap up.
Okay. Thanks, John. Thank you to everyone, and particularly our audience for sticking with us. Apologies, we've run over a few minutes, but I'm sure you've enjoyed the session. As I said, it's billed as information. It's the start of a 2-year program. So this is not the first and last time you'll be hearing from us about metamaterials. We're going to continue to make sure we're engaged with you, engaged fully on our programs. So I'll say thanks to the speakers. Very excellent a range of presentations. You've heard about UK excellence in academic base and the reason why we have the confidence to make sure we carry on this process of commercialization. You've heard about how, in some way, both academics and businesses are beginning to exploit the promises that metamaterials make. Very exciting presentations. And you've heard the shared experience of how to go through the commercialization process. As daunting as it may be, there are some pointers there that the network needs to take on board, because this is about a shared journey to make the work, the hard work in the process much lighter for all of us. So let's work together to do that. And you heard from John about the role of design. John shared the experiences in other areas, but we can actually engage with our process to get metamaterials into the consciousness of designers, because believe it or not, they do make a difference in materials choices for real life products. And we want them to be aware of metamaterials, to understand the opportunities metamaterials can offer. So thank you, John. We will engage with MADE in this process. So all the wisdom we've had, all the ideas we've had, all the evidence that metamaterials is here and is for the future will guide us as we put our programs together to engage with you over the next 2 years. So let's work together. You'll hear more about our detailed plans. Now that we've got your contact details, we'll make contact with you and we'll share with you the plans we have and share with you the next event, which will be very interactive. You have your chance to speak out. But you do have a chance this afternoon. Don't forget, you've got a break, and 1 o'clock, we've arranged via Meetimojo for you to have a bit of collaboration space, breakout sessions on one-to-ones but you need to book these. So go to the link that's been given to you and book your time with the expert, with each other, and have a good networking session. So thank you, everyone. Till next time. Thank you.